For centuries, the image of the alchemist has been one of obsession. These early scientists toiled in soot-stained laboratories, driven by a singular, maddening goal: the transmutation of base metals into gold. They sought the philosopher's stone, a legendary substance capable of perfecting the imperfect, of turning lead into the divine metal. They failed, of course. The laws of nuclear physics were not theirs to command. Yet, in a twist of irony that history often enjoys, the true golden revolution of the 21st century did not come from creating more gold, but from fundamentally changing the gold we already have. It came not from adding weight, but from stripping it away, atom by atom, until only a single, shimmering layer remained. This is the story of Goldene. In the quiet, sterile corridors of Linköping University in Sweden, a team of materials scientists has achieved what was long considered thermodynamically impossible. They have forged gold into a two-dimensional sheet, a material only one atom thick. In doing so, they have not only created a new material, but have unlocked a realm of physics and chemistry that transforms gold from a passive, noble metal into a dynamic, semiconducting powerhouse. This discovery, announced to the world in 2024, is not just a curiosity. It is a gateway to a new era of electronics, green energy, and nanomedicine. It is the modern alchemy, where the transmutation changes not the element, but its very soul. To understand the magnitude of this breakthrough, we must first understand the element itself. Gold, atomic number 79, is the metal of paradoxes. It is cherished for its beauty, yet it is chemically boring. In its bulk form, the form of wedding rings and bullion, it is the most noble of metals. It does not rust, it does not tarnish, and it refuses to react with almost anything. This inertness is why it has been used as money for millennia. A gold coin from Roman times shines as brightly today as it did when it was minted. However, in the world of catalysis and advanced electronics, boring is a problem. You want materials that interact, that facilitate reactions, that conduct electricity in controllable ways. Bulk gold is a great conductor, but it is a dumb conductor. It lets electrons flow freely, but you cannot easily switch that flow on and off like you can with silicon. Furthermore, gold is expensive. Using heavy solid chunks of it for industrial processes is economically ruinous. For decades, scientists looked with envy at carbon. Carbon is a chameleon. Arrange it one way, you get soft graphite, another, hard diamond. But the real revolution happened in 2004, when researchers at the University of Manchester isolated graphene, a single layer of carbon atoms arranged in a honeycomb lattice. Graphene was a wonder material, stronger than steel, more conductive than copper, and transparent. Its discovery triggered a gold rush for other two-dimensional materials. Scientists synthesized silicene from silicon, phosphorine from phosphorus, and germanine from germanium. But gold? Gold remains stubborn. The problem lies in the atomic bonds. Carbon atoms are happy to form strong, directional, covalent bonds with their neighbors in a flat plane. Metal atoms, however, are communal creatures. They prefer metallic bonding, a state where electrons are shared in a loose cloud among a non-directional cluster of atoms. Gold atoms want to clump together. If you try to make a thin sheet of gold, the surface tension pulls the atoms inward, causing the sheet to curl up and collapse into a nanoparticle. It is like trying to flatten a drop of water into a sheet. Physics wants it to be a sphere. For years, 2D gold was the white whale of materials science. Some claim to have made it, but their sheets were always supported on a substrate, unable to exist freely, or were actually several atoms thick. The scientific consensus was leaning toward the idea that a freestanding, single-atom layer of gold was thermodynamically unstable. It simply shouldn't exist. Enter the team at Linköping University, led by Professor Lars Hultman and researcher Shun Kashiwaya. Their discovery of Goldene was not a straightforward path of engineering. It was a journey of serendipity, ancient wisdom, and rigorous chemical detective work. The story begins not with gold, but with a family of materials known as max phases. These are layered ternary carbides and nitrides that combine the properties of metals and ceramics. They consist of layers of a transition metal, an A-group element, and carbon or nitrogen. The structure is like a nanoscopic sandwich. Layers of tough ceramic are separated by thin layers of the A element. The Linköping researchers were experts in these materials. They were working with a specific ceramic called titanium silicon carbide. Their goal was mundane. They wanted to improve the electrical contacts on this ceramic by coating it with gold. They deposited gold onto the surface and heated it, expecting the gold to sit on top like a layer of paint. But when they looked at the interface under an electron microscope, they saw something strange. The gold hadn't just sat on top, it had disappeared into the material. At high temperatures, the gold atoms had diffused into the ceramic, kicked out the silicon atoms in the layers, and taken their place. The result was a new material, titanium gold carbide. This mechanism is known as intercalation. It is a bit like sliding a new card into a deck and pushing an old one out. The researchers realized they had created a laminated material where single layers of gold were trapped between layers of titanium carbide. The gold was there, organized in a 2D sheet, but it was imprisoned within the ceramic crystal. The challenge was now one of liberation. How do you remove the titanium carbide bread from the sandwich, leaving only the gold filling intact? This is where the story takes a turn into the annals of history. Standard chemical etchants used to dissolve ceramics often involve hydrofluoric acid, a nasty, bone-dissolving chemical that is dangerous to work with and would likely destroy the delicate gold layers or cause them to clump up immediately. Shun Kashiwaya began hunting for an alternative. He needed a chemical that was selective, something that would eat titanium carbide but leave gold alone. His search led him to a technique that was over 100 years old, rooted in the traditions of Japanese metallurgy. In the art of Japanese swordmaking, and later in the analysis of steel microstructures, smiths and metallurgists used a specific concoction to reveal the grain and carbon content of the metal. Known as Murakami's reagent, it is a mixture of potassium ferrocyanide and potassium hydroxide. Murakami's reagent was famous for etching carbides. In the steel industry, it is used to attack the iron carbide particles to make them visible under a microscope. Kashiwaya wondered, if it attacks iron carbide, could it attack titanium carbide? And more importantly, would it spare the gold? It was a gamble. He tried different concentrations of Murakami's reagent and different time spans for etching. One day, 1 week, 1 month, several months. The process was agonizingly slow. The reagent gently chewed away at the titanium carbide layers. But there was a problem. In the presence of light, potassium ferrocyanide can decompose to form cyanide ions. Cyanide is famous for one thing in metallurgy: it dissolves gold. This is the basis of the cyanide process used in industrial gold mining. If they etch the material in the light, the very chemical intended to liberate the gold would instead dissolve it, leaving them with nothing but a beaker of toxic liquid. The solution was simple, but strictly necessary: darkness. The researchers had to conduct the entire etching process in the dark, turning their modern laboratory into a photographer's darkroom. They tweaked the formula, lowering the concentration and extending the time. They found that a low concentration of Murakami's reagent, left to work for weeks in complete darkness, successfully etched away the titanium and carbon. But they weren't done. Even with the ceramic removed, the gold layers faced the old enemy: surface tension. As soon as the supporting layers were gone, the gold atoms would want to curl up and bond with each other, destroying the 2D structure. To prevent this, the team added a surfactant, a soap for atoms. They used cysteine, a simple amino acid. As the titanium carbide dissolved, the cysteine molecules rushed in, latching onto the exposed gold atoms. This prevented the gold sheets from colliding and fusing. It stabilized them, keeping them floating in the solution like sheets of paper in water. When they finally placed a drop of this solution under a transmission electron microscope, they saw it: distinct, isolated sheets of gold. They were irregular in shape, like torn leaves, but they were unmistakably gold, and they were unmistakably two-dimensional. They named it Goldene. The suffix "ene" is a nod to graphene, acknowledging its place in the growing family of 2D materials. But Goldene is distinct. Structurally, Goldene is not just a slice of bulk gold. In a bulk gold crystal, atoms are packed in a face-centered cubic lattice, where each atom is surrounded by 12 neighbors. In Goldene, the atoms are arranged in a hexagonal lattice, and each atom has only 6 neighbors. This reduction in coordination number is catastrophic for the material's old identity and birth to a new one. In bulk gold, the electrons are free to roam anywhere, which makes gold a metal. In Goldene, the electrons are confined to a flat plane. This phenomenon, known as quantum confinement, fundamentally alters the energy levels of the electrons. The most shocking result of this confinement is that Goldene is a semiconductor. This is a statement that would make a classical physicist blink. Gold is the archetype of a conductor. Yet, when thinned to a single layer, a band gap opens up. The electrons require a specific amount of energy to jump from the valence band to the conduction band. This property is the foundation of all modern electronics. It is what allows silicon to switch currents on and off to create binary logic. Bulk gold cannot switch. It is always on. Goldene can switch. This immediately puts it in the running for use in next-generation transistors, potentially allowing for electronics that are faster and more conductive than silicon, yet chemically inert and stable. Furthermore, the lattice of Goldene is compressed. The researchers measured a 9% lattice contraction compared to bulk gold. The atoms are holding on to each other tighter, compensating for the lack of neighbors above and below. This creates a strain in the material that can be exploited for strain engineering, tuning the properties of the material by stretching or compressing it. Perhaps the most immediate and impactful application of Goldene lies in catalysis. A catalyst is a substance that speeds up a chemical reaction without being consumed. Gold, in its bulk form, is a terrible catalyst because it is so unreactive. However, it has been known for some time that gold nanoparticles are excellent catalysts. This is because the atoms on the surface of a nanoparticle are frustrated. They don't have enough neighbors, so they are eager to interact with passing molecules. Goldene takes this to the ultimate limit. In a sheet of goldene, every single atom is a surface atom. There are no inner atoms hiding in the bulk. This means the surface area to volume ratio is theoretically infinite relative to the thickness. Every atom is exposed and ready to work. This has massive implications for hydrogen production. Currently, humanity is trying to shift toward a hydrogen economy. We want to split water into hydrogen and oxygen using electricity. This process requires catalysts. Platinum is the current king of hydrogen evolution, but it is prohibitively expensive. Goldene, with its unique electronic structure, shows promise as a hydrogen evolution catalyst. The undercoordinated atoms on the jagged edges of the goldene sheets act as active sites where protons can grab electrons to form hydrogen gas. Because goldene is so thin, you need very little of it. A gram of goldene has a surface area that covers a vast field. We could potentially replace solid platinum electrodes with electrodes coated in a microscopic dusting of goldene, drastically reducing the cost of green hydrogen. Then there is the holy grail of climate tech, CO2 conversion. We are pumping carbon dioxide into the atmosphere at dangerous rates. Capturing it is one thing, but what do we do with it? Ideally, we would turn it back into fuel or useful chemicals, a circular carbon economy. Gold nanoparticles are already known to reduce CO2 into carbon monoxide, which is a useful feedstock gas. Goldene, with its tunable semiconductor properties, could be even better. By adjusting the charge on the goldene sheet, chemists could fine-tune the reaction to produce not just CO, but more complex hydrocarbons, like methane or ethanol. The goldene sheet acts as an electron pump, grabbing stable CO2 molecules and destabilizing them so they can be rearranged into fuel. The potential extends into medicine. Gold nanoparticles are already used in lateral flow tests and are being investigated for cancer therapy. Goldene offers a new geometry for these applications. Its flat shape and huge surface area could allow it to carry massive payloads of drugs into the body, or act as ultra-sensitive biosensors that detect disease markers at the single molecule level. The synthesis of goldene is a proof of concept that opens the floodgates. If we can make 2D gold, what else can we make? The periodic table is full of metals. The Linköping team and others are already eyeing the platinum group metals, like iridium, platinum, and palladium. A 2D sheet of platinum, perhaps called platinine, would be the ultimate catalyst for hydrogen fuel cells. A 2D sheet of silver, silverine, could have unmatched optical properties. We are witnessing the birth of a new family of materials, metallines. Just as the isolation of graphene led to a revolution in carbon chemistry, goldene is leading a revolution in metal chemistry. We are moving from the Stone Age of bulk metals, where we simply dig rocks out of the ground and melt them, to the architectural age of metals, where we design materials atom by atom. There is also a profound sustainability angle. Gold is a finite resource. Mining it is destructive. It displaces communities, destroys ecosystems, and uses toxic chemicals like cyanide and mercury. By maximizing the efficiency of gold, by making every atom count, goldene allows us to do more with less. Imagine a future where the gold in your electronics isn't a thick plating, but a single atomic layer. The amount of gold required to build a smartphone or a computer would plummet. We could stretch our planetary reserves of precious metals centuries further. The discovery of goldene is a triumph of curiosity. It started with a mistake. Gold disappearing into ceramic was solved by looking backward to ancient Japanese sword etching, and resulted in a material that points us forward to quantum electronics and green energy. It reminds us that the periodic table is not a finished map. It is a terrain that we are still exploring. We thought we knew gold. We wore it, traded it, and buried it in vaults for thousands of years. But we only knew its face. We are only now meeting its spirit. Goldene is not just a new material. It is a new way of seeing matter. It proves that even the most familiar, stubborn, and noble of elements can be transformed if we simply change our perspective, or in this case, our dimension. The alchemists of old would be proud. They didn't need the philosopher's stone to create gold. They just needed to peel it.